Hello, everyone. Good morning. I hope you're nice and awake. My name is Liz Fong-Jones, and I am a staff site reliability engineer on the customer reliability engineering team of Google Cloud. And I've been at Google for over 10 years, and I've worked on 8+ teams at Google, all SRE teams. And I've learned that there are a lot of lessons you can take from team to team. And I've realized that there are a lot of really cool things that we should really share with the world that really make your life easier as an SRE, that make your life easier when you're dealing with outages and incidents. Adam.
My name is Adam Mckaig. I've been at Google much less time than Liz, only around 18 months. But I've been in the industry. I've been an SRE DevOps type person for something like 8 or 10 years now. The reason that I wanted to give this, can we do the next one? The reason I wanted to talk today was when I joined Google, a lot of the techniques and tooling that I learned immediately as an SRE kind of blew my socks off. I'd been doing essentially the same job for about, again, 8 or 10 years, but the way that they were doing that at Google was completely amazing. And looking back, I realized I could take a lot of what I'd learned, a lot of the techniques I was using, and I could have been doing those, making my own life a lot easier for a very long time. None of what I was learning was specific to Google. So that's what I want to talk about today. I want to show some of those techniques. Hopefully, and it'll make your life a little easier. Really, the target audience of this talk is myself 18 months ago. So where possible, we're going to call out the open source and proprietary tools that you can use to do this sort of thing. But we're going to use an internal tool called Panopticon to demonstrate these techniques. And notably, a lot of these features are also coming to our benefactor in the form of Stackdriver. So look out for that.
So I just want to level set a little bit. And why is this not advancing? That's not good. Just make sure my laptop hasn't crashed. My laptop has not crashed. There we go. OK. So let's go ahead and level set and talk about what our expectations are of who would find this talk useful. So we're assuming that most of the folks here are interested in debugging distributed systems. So we assume that you have a service that's composed of many different microservices, and that you might have your microservices orchestrated somehow running across many, many different hosts. So kind of the problem that we run into is that you have a high combination of cardinality and number of metrics. So something like your number of metrics and your number of hosts or replicas is greater than 1,000 when you multiply them together. And furthermore, we think that you might have to debug things across multiple different regions, right? You might have to figure out where exactly is this problem happening. Is it in one place? Is it in another place? And finally, we think that batch systems are really interesting, but batch systems for the moment are out of scope for what we're talking about. And you can ask us questions about that later as far as how these techniques apply to batch systems. So let's just level set again on another thing. How many of you, raise your hand if you have service level objectives for your service. OK, that's about half the room. Raise your hand if you are alerting when your service level objective is in danger. OK. Have you had a problem where you're alerting, you've turned off all those noisy little individual machine alerts, and you suddenly can't find where's the problem because you get this top level alert that says users are seeking pain, and you don't know how to debug it? So this talk is for you. So if you have users that are seeing errors, and you have your service level indicators impacted, and then your error budget starts getting burned, and then you get paged. So now what do? We need to prioritize the speed that we mitigate and recover our service. And I want to go over the conceptual model that we have of where do people spend their time when they're debugging. So your service might be working fine. It's meeting its SLO. And then a fault happens somewhere hidden deep inside our system. We don't know where it is right now. But the service level indicators are impacted. Users are feeling pain and are alerting fires. And now we have to figure out what's going on. So the first thing that we need to do is we need to figure out what's the blast radius. Is there something really quick that I can do to mitigate the impact? And if that's not the case, then I need to go ahead and formulate a hypothesis. What do I think is going wrong? Because it doesn't make sense to fix a problem that isn't real. So you have to figure out what do you think is going wrong. And then you have to test it, right? You have to figure out, is this actually the problem? And ideally, your first guess is right and your hypothesis is confirmed. So you can go ahead and develop a fix, and then finally we want to just verify that our fix worked, verify that our service level indicators went back to normal. And then we're back to meeting SLO and our service is running in nice homeostasis. Great. But that's unfortunately not the way that it works all the time. Unfortunately, a lot of the time our hypotheses are wrong or our fixes are wrong. So you wind up spending a lot of time either formulating a hypothesis and testing it, or developing a fix and then testing it, and then going back to square one when that doesn't work. So we think that you can really improve your resiliency if you are able to increase the speed of that loop, if you are able to formulate those hypotheses faster. So it's kind of, I know in control theory, it's kind of the orient, observe, act, decide loop. So that's kind of another term for this loop. And we'd like to work with you a real example and show you 3 of our best practices. So the first technique is called layer peeling, of being able to drill down to find a problem. The second technique is called dynamic data joins, of being able to test a hypothesis by finding out, even if you didn't compute it in advance and know you'd want to test that hypothesis, being able to join your data together to get the results that you need. And then finally, the technique that we'll show you is exemplars, which is a technique of bypassing the first 2 steps and jumping directly to having a hypothesis you can quickly test. So Adam, you get paged. Here you go. Ringing pager.
What a lovely start to my day. So we need to formulate some hypotheses here. I just got paged, and I'm waking up, I'm getting out of bed, and this is all the information I have at this point. So it looks like something is going wrong in US West 1, one of our regions. And this alert says that we are seeing too many slow queries. Now, that's a pretty vague alert, and we tend to keep our pages pretty vague by default because it's a little dangerous to be conveying too much information because it could be wrong, it could be misleading. So it's my responsibility at this point to dive in and see if I can figure out what's wrong. Now, there are a lot of reasons that we could be seeing too many slow queries. What that actually translates to is that one of our SLOs is in danger of being violated. By too many, I think we're using 98th percentile latency here, and our SLI, our objective, is about 100 milliseconds. So there are a lot of things that could have gone wrong. It could just be that our entire service is completely broken, and this is the first thing I'm hearing about it. Or it could just be that we have a few outliers in the top 2% which are causing latency. Either way, we're going to have to track down the replicas, which may be all of them, maybe one of them, which are causing the problem. So the first technique I'm going to use is the one I reach for almost every time out of the box, layer peeling. What this means is we start at the very top level, the highest level, which is the same level that our alerting works on. Of course, it wouldn't do for us to be paged every single time one of our replicas, as Liz mentioned, we have thousands of these replicas around the world, if one of them was going wrong. So we have to start with a very high-level aggregated metric, the 98th percentile latency in one of our regions, in this case, US West 1. So I'm going to start there. I'm then going to drill down into that region and see if I can find out something about those replicas which they have in common. In this case, I'm going to drill down into the zone and see if I can discover which availability zone in that region is causing the problem. Once I've isolated that, I'm going to jump into the individual replicas in that zone and see if I can track down the one that's causing the problem. So here's Pecan. It's a panopticon. This is the metric, the raw data, which caused the alert in the first place. You can see a few minutes ago it crossed some kind of barrier. You good? What's up?
Yep, I'm just, oh no, I broke it. I'm trying to get the laser pointer view on, sorry, so we can actually see what's going on. Unfortunately, that did not work, so we're just going to do that, and we're going to have to not have speaker notes, and it'll be fine.
That's okay.
There we go. Now we have the laser pointer view. So if you need to, you can.
Thanks, Liz. Okay, so we can see roughly here that I got paged about 10 minutes ago when this line crossed our SLO at 100 milliseconds. It's important to note this is all fake data. Our SLO isn't really 100 milliseconds, that would be far too slow. So I can't really tell what's wrong based on this graph. This tells me no useful information apart from something is wrong. So I'm going to pop open the sidebar in Pecan, and this is a query editor. One of the important takeaways from this is that the tool that we use to visualize our data is also the tool that we use to construct these queries in the first place. And so when we're debugging, it's really helpful to be able to modify the query and slice and dice it different ways so we can drill down without having to open up some different tool. So the first thing I'm going to do is I'm going to remove that filter you can see that says only show me data from US West 1, because what I want to check is that it could be that every region is broken. It could be our whole service is failing. But US West 1 was the first one I was paged about. So we can see here that the other two zones, I think it's East and Central, or the other two regions rather, East and Central, are still well below their SLO. So this isn't a problem which is global. This looks like a problem which is isolated to one region. So I'm going to go back. Oh, we added this one last night and I forgot about it, sorry. The obvious question here is why don't we skip all of this and drill down into the individual replicas and just look at all of the data all at once and use our eyeballs as humans to pick out the failing replicas. And here's why. It's because if I skip all of this and show you the latency for every single one, it's just a completely hopeless jumble. Maybe you can pick out the outliers there, but an important thing to note is that just because one replica is going wrong, say it has higher elevated latency compared to all of its siblings, that doesn't necessarily mean it's the problem. It could just be on a slow machine, and it could not be receiving any traffic. It could be well within our SLO, even though the replica is broken. So we're going to go back to bisecting. That was a brief digression. So back to where we started. We know it's not a global outage at this point, so we're going to focus on US West 1. The first thing I want to do is replace this very high-level aggregation with the underlying query which generated this aggregation. Now, if you have a look on the left, you can see that there are 3 steps. Oh, thanks, Liz. There are 3 steps in this query. We're just fetching the data. We are aligning the data just to snap it to the grid, and then we're grouping it, which allows us to view the individual regions separately without jumbling them all together. But we can click on this link, replace with, I forget what it says, replace with source or something like that.
Replace with definition.
Yes, that's it. Which allows us inside of Pcon to remove this query and replace it with the query which was used to generate this data in the first place. So take a look at the query steps on the left. Those have now expanded into the underlying query. If we were doing this live, you'd see that this query was a little bit slower than the previous one because we had to go off and fetch a lot more data and then aggregate it at query time to generate this. We wouldn't want to do this for all of our alerting, of course, because you can probably imagine if we wanted to take the 98th percentile every time we wanted to check whether we were within SLO by reaching out to every single one of our instances and asking them what their latency was, that would be incredibly slow. But we can do that at query time here.
And there's also another advantage here as far as conceptual complexity. The idea that we can replace that one query here and then be able to expand it and not have to keep the full set of all of these steps in our head and just look at this 3-step pipeline. But now we need to drill down into the details. So now we're in this 4-step pipeline here.
Right. This gives us a lot more flexibility than we had previously. So we can scroll down to the bottom of this query and we can group it differently. The data doesn't look terribly different here, so let me skip back and forth a few times. This is the latency SLI for the region, and then if I group it differently at the bottom by selecting the zone, then this is the latency for those individual zones inside of our region. Now, I was a little lazy and I left the horizontal line for the 100 milliseconds, but it doesn't really apply. We don't actually have an SLO for those individual zones. We don't really care if a zone is over 100 milliseconds because we don't guarantee to anyone that it won't be. The region is. So you can see something interesting here. One of these zones is consistently responding at above 100 milliseconds, and it doesn't seem to have caused us any problem. That might just be because there's little enough traffic going to it that it didn't impact our overall SLO. We could drill down into that, see if we can find out what's wrong there, but it's sort of beside the point, because we can very clearly see that one of our zones, the latency has started elevating about the time I was paged. So we can pretty much guarantee that that's where the problem is. So we can pop open the sidebar and just check out which zone is this. And I think it's US West 1A. It looks like it's elevated. So we're going to use that information to drill down a little bit further into the query. Excuse me. You can see we've added another filter here. So now we're just looking at that one line. This doesn't tell us anything more interesting. But if we scroll down to the bottom, the last step of this query is we take a distribution and we convert it using a percentile operation, a percentile 98 operation, into a double. Now, the reason we do this, of course, is because our SLIs are expressed in terms of percentiles. I'll show you the distribution in a minute, but it wouldn't do to tell the computer, alert me if things are looking too slow. You've got to put absolute numbers on it, and for that we've got to convert it into an actual number. But when I'm investigating the problem, there's a lot more information I can find if I look at the underlying metric. So I can remove this step from the query and be presented with the underlying data. I don't know if you can see, it's a little small, but the last type on our query now is distribution. It's no longer double. So this is the distribution of all of the queries, or the response time of the queries inside of US West 1A, where we know our problem is. And this is one of the features of Peakon that really blew me away initially. There's so much information that you can derive from this chart or this heat map that you can almost tell what the problem is right here. Oh, I'm sorry, am I talking too quietly? Never heard that one before. Okay, so if we have a look at the lines which are overlaid, they're a little bit. Is that okay? Welcome to the presentation, those of you that couldn't hear before. So it's a little difficult to see because it's yellow in the middle of our chart is yellow, but we have 4 lines which are overlaid on here. One of them is the 50th percentile, one is, I think, the 98th percentile, or rather the 90th, the 98th, and the 99th percentile overlaid on that. And so what we can see is that the 50th percentile hasn't really moved at all.
By the way, yellower is more hot, so there are a lot of queries in here in this kind of center of mass, and then there are some queries over here that are slower, right? That's kind of the essence of the flame graph is overloaded. We call these flame graphs, which is confusing, but the distribution graph has intensity to show you how many queries are there.
That's right. I didn't think to ask when I joined, but these colors don't really make much sense in hindsight. I suppose the flame metaphor does work. Like, the brighter the color, the more queries we have in this bucket. And you can read this. You can read this a number of different ways, but essentially, Liz is right. Like, brighter means there are more queries in this bucket. So the majority of our queries are still in these buckets, right in the middle of the chart. That hasn't really moved at all. So what we do know is that it's not that US West 1A is just completely broken and the latency has risen for all of those queries. But when the page started, we could see that the outliers right at the top, which were previously over 100 milliseconds anyway, have actually risen quite a bit. They're all the way up to 140 milliseconds at the 99. So we're going to go back at this point. We've learned something interesting, that we have to track down a subset of the replicas in US West 1A. So we're going to go back to the previous way that we were looking at the 98th, because again, that's where we're really alerting. We're going to drill down again from the zone into the actual replicas inside of that zone by clicking the same button, replace with definition. And now we can see something really interesting. Now we're lucky that the zone, US West 1A, is small enough that we can reasonably plot all of the instances in this zone. And you can see there's a couple of outliers pretty clearly. Am I still too quiet?
Yeah, let me just move your microphone up here.
No.
Try that.
Thanks, Liz. Everyone hear me okay? Yeah. Silence at the back? All right, good. Sorry about that. Okay, so we can see here there are a couple of pretty obvious outliers. The zone is small enough that we're able to reasonably plot all of these on here. But a brief sidebar. In some cases, it's just not. We may have one of our really big zones which are going wrong. Some of our US central zones are far too big for us to be plotting like this, and so there are tools inside of Peakon, if there were too many streams here, for us to pluck out some of the streams and to filter this down a little bit further. But we're not going to get too far into that today. So I'm going to filter this down. Again, you can see this is just one of those outliers which I was previously seeing. I would use the sidebar to pop out and find out like which replica is this. In this case, it's replica number 4. So I'm going to filter this down to replica number 4, and then I'm going to do the same trick that I just did by scrolling down to the bottom and removing the percentile operation. So now I'm looking at the distribution of all of the queries which are hitting replica number 4 in US West 1A. And here we can see a totally different thing from this distribution. Now, unlike the previous distribution where there was still some number of queries which are at the bottom, and they hadn't really moved. All of the queries which are hitting this have elevated. The 50th percentile even has gone well above the target SLI. So from that we can tell this replica is basically broken. The immediate mitigation would be, let's just kill this, because of course these are cattle. So just to recap, there's no way that we could have gone straight from the raw data, looked at, or straight from the high-level aggregation, looked at the raw data, and then plucked those out by eye. We just couldn't have done it. There were too many of them. So instead, we bisected the problem into smaller and smaller groups of replicas until we could reasonably tell which one was actually broken. So that's layer peeling. The second strategy I'm going to use is dynamic data joins. Now, at this point, let's posit that we've already mitigated the problem. We've killed those replicas, and they've come back to life using, they've come back to life, and they're behaving as they should. They're within SLI. So this will be a reasonable time to close this outage. But I'm going to spend a few more minutes, thank you. I'm going to spend a few more minutes trying to track down what the problem is, so I can really close the outage, so I can be sure it's not going to happen again, and I can go back to bed. Now, bisecting the problem is really nice if we can reasonably assume that some of the replicas which we're using, some of the replicas are broken. Now, there's another strategy. Am I still too quiet here?
Look there, not there.
Oh, okay, sure. Yeah. Oh, that's it. I'm speaking over there, aren't I? Huh. We also have a screen down here. So there are a lot more tricky problems that need a little bit more information than can be found in the actual alerting metric. We can include a little bit of information in the metrics which are alerting, like the zone and the region and the replica ID, so we can find where those replicas are. But there's a ton more information that we might want to use during this outage. One of the really nice things about jobs at Google is that every single one of them, every single task, exports a tremendous amount of data. So it would be a shame not to be able to use that while we're debugging. So we're going to take those additional informational streams and we're going to join them with the stream which we started with, the latency stream. So I'm going to open up a different tab in Pcon, a brand new query. And I'm going to try and pluck out the kernel version. I have a theory that this might be something related to the problem, because let's say before I killed those tasks, I happened to notice that they were running a slightly old version of the kernel. So my hypothesis is that that might be something to do with the problem. So I'm going to make an ad hoc query here. I'm going to okay, so I turn this off?
They'll fix it at the switchboard. Just make sure this is on, which is this. There you go.
Thank you so much. Okay. I'm much better at computers than I am at microphones.
Hold it right there.
Right here? Okay. Okay, so let's try this again. So I've made a query here which has plucked out the kernel version of all of the tasks which are running my job. Now, this information isn't terribly useful by itself. I can tell that there are some jobs which are running release number 1111. This is just an abstract, like a release number, not an actual kernel version. And there are some which are running a lower version, but this isn't terribly useful. So I need to group this together. If I jump down to the bottom of my query, I can do that in the same way that I modified the last query. Now right here. So I've taken those raw streams which are being output, one for each of the jobs, and I've grouped them together using a count operator by region. Yeah. So we can see, by kernel version rather. So we can see that there's a huge number of kernels which are running the latest version, and there are a few stragglers there right at the bottom of the chart. Now, I can take this information and I can join it at query time with the latency information I was seeing, which I was working with previously. So here it is again, totally useless. But I can take these two queries and join them together. So just to skip back and forth between the two slides, this is the latency query, and when I take the first query and join it together, you see the query gets a little more complex on the left, because now there is an additional column that you can see on the right. So we're now looking at the latency, which is on the far right, and we also have the kernel version annotated for each of those tasks. We still can't see which is causing the problem, but
If we were to add a group by operator at the bottom of this, we now have the power to group the latency information by the kernel version. And this yields something much, much more interesting, I think, which is that one of these kernels is exhibiting much higher latency about the time I got paged. If I pop open the sidebar, I can see my hypothesis is confirmed, and it looks like we have some old kernel versions which are running in production, which suddenly started exhibiting a lot higher latency. Now, this is a really good time for me to, I don't know, open a bug, to update our alerting, to make sure we're not running these in future, and to maybe have a look and see if I can find any other tasks which are running this old kernel before I can really close this issue. So that's dynamic data joins. The point which I'd like everyone to take away from this is that you can only go so far by taking metrics like latency metrics and adding more tags and more fields to them. You can add a few of them, but before long it becomes far too unwieldy. We couldn't possibly include every single piece of information with every single metric. So what you should really be thinking about doing is exporting a lot of peripheral information, like the kernel version here, as much as you have really, and then joining it back together with the alerting metrics at query time, if possible. Liz?
So Adam and I have spent the past 20 minutes talking through the process of gradually debugging things by going through step by step by step and drilling down until you find the answer. But I'm going to show you something really cool that lets you get to the heart of the issue within a few minutes. And the way that we do this is that we make your distributed tracing actually useful. We make your high cardinality data tags and data streams actually useful. How many of you are using distributed tracing right now? Raise your hand if you use distributed tracing. Okay, how many of you have trouble finding the right distributed traces to look at? Yeah, it's a common problem among the handful of people that are using distributed tracing. How many of you are not using distributed tracing because you don't think it really adds that much value or it's too complex, right? How many of you are not using distributed tracing? Raise your hands. Okay, so the idea is that if you use sampling, you can get an idea of where is a problem happening by finding specific traces or specific high cardinality tags associated with bad behavior, and then drawing patterns using your own human eyes and figuring out what do I think is the common element shared between all of these, rather than kind of hunting and pecking and drilling down in detail. So you can use your graphing tool of choice. Some of you use Grafana. We obviously use Panopticon. But the critical technique here is that you need to be able to not just plot a distribution or a heat map, but you also need to be able to see which samples share the same tags. Are there any samples associated with a given histogram bucket? When I talk about a histogram bucket, by the way, just to refresh everyone's memory, a histogram bucket is going to be one of these little slices here. It's kind of the idea of a horizontal amount of time and a vertical range of values in your histogram. So going back, when you're talking about highlighting which buckets have samples, you want to be able to see for each bucket, does it have a sample or not? What is the sample? What are the details on that sample? So let's talk about the tagging technique of being able to look at those high cardinality tags. So if you remember what Adam and I were saying earlier, right? Like there are way too many tasks for us to look at the global picture and see each individual task. But one of the cool things is that we can wind up looking at this global histogram, right? This is the histogram across all of our tasks globally. And we can go in, we can say, I want to keep some of those high cardinality tags. So for each bucket, I want to save at least one example of a task ID in a region in a zone corresponding to a task that exported something in that histogram bucket. So if I do that, what does that give me? Well, first of all, it gives me a little, it's really hard to see, but there's kind of a little green dot at the top of each of these buckets saying, hey, I have some data here for you. And if I hover over one of these, what I'll find is that it highlights everything that shares the same source task data, that has all the same tags. So I can hover over one of these things, and I can see, hey, wait a second. There are a whole bunch of other high latency data points that also come from that same place. And then I can click on it, and it will show me and tell me exactly where that's happening. And it'll tell me, this is task ID 4 in US East 1A. And that lets me immediately go and see and look at the logs at the exact point in time that that task started exhibiting that behavior. So if I were to look at, I think, like 9:35 a.m. at that task, I would get a good idea of knowing where to start debugging right away. Now, of course, I'd still need to confirm the theory, but that shortened the amount of time to identify a hypothesis as to what was going wrong, and get it down really quickly. There's another thing that you can do besides getting the high cardinality tags, which is if you use distributed tracing, you can actually get an example of what is causing your black box SLI to fail, or your synthetic SLI to fail. So we've instrumented, this is, by the way, from Cloud Bigtable. We have a black box prober that goes and attempts to ping the Cloud Bigtable and issue a read or a write or an in-memory read. And we've told it, instead of sampling like something like 1 in a million traces, we've told it to sample 1 out of 100 of its synthetic RPCs will be sampled by our tracing system. Because we know that the volume of this is going to be consistent and that the storage cost is not going to be too high. So this means that we can actually look at our SLIs to see what's causing an SLI excursion. So this is what the graph might look like. I might have some amount of synthetic RPCs that I'm issuing. And what I might notice is that the 99th percentile latency starts creeping upwards. And if I want to stay at less than 100 units, then I might get alerted somewhere in here. And having the detailed distribution heat map info is really, really critical. Why is it critical? Well, if we look at the heat map here, we can see that there are some queries that are taking 1,000 units, and that there are more and more and more of them, and that's the thing that's causing my 98th percentile or 99th percentile latency to go up. And not only that, I can see a little T icon corresponding to a trace associated with some of these buckets. Not all of the buckets, but some of the buckets. So I can say, show me an example of a query taking 1,000 units. And it will do that, and it will give me a pointer to the exact trace that I'm looking for inside of Dapper, our distributed tracing system internal to Google. So if I go ahead and click on that, what does that give me? Well, it gives me the top level trace, which is not really that useful. Remember, the value is distributed tracing. So I can go ahead and expand that out. And if I expand that out, I can see that it's actually a problem inside of Bigtable. And specifically, I can tell right away that the problem is in the distributed file system underlying Bigtable. And the problem is that I'm not able to finalize files and commit the log. So that gives me a really great idea of right away, where do I need to look for the problem? Maybe I need to page Colossus SRE. Maybe I need to go and debug the closed stripe latency, right? But if I had gone and looked at our dashboards to start with, we have like 50 dashboards associated with Cloud Bigtable. Each of them has 10 or 20 different graphs on it. How long do you think it would take me to look at 500 graphs to figure out which one is squiggling and correlating at the same rate? Or maybe most of them are doing that, and any kind of correlation is not going to really help me. So being able to jump directly to this gives me a really great idea of what's going on and gives me an intuition as to what I should further look into. So a quick pitch from our from Stackdriver. This is Dapper is an internal Google tool, but you can also get distributed tracing through Stackdriver APM and Stackdriver Trace. So this is what the distributed trace view might look like inside of Stackdriver Trace. So how do we actually do this on the inside? So this is kind of an overall system diagram of Monarch. The idea is that we have some kind of a monitoring library embedded in each target replica they're monitoring, and that they stream the data to collection leafs. And the collection leafs write the data to a repository. So that data might include the various histogram buckets, like what's the width of the bucket, what's the height of the bucket, how many samples are in that bucket for each task, and is there an exemplar associated with it? Is there a trace associated with that bucket? And then when it comes time to aggregate, what I can wind up doing is I can wind up either saying, you know what, there are multiple examples associated with this bucket, I'm just going to randomly pick one, or it will let me say, you know what, I'm throwing away a bunch of that task tag data, and I want to make sure to save at least one copy for each bucket. So that's kind of the magic, is in the aggregation layer is where exemplars really shine, because they let you winnow your data but still be able to see the trees in the forest. So how does this work in pseudocode? So you might have inside of your monitoring collection library, if you're logging in latency, you might want to check, am I supposed to collect an exemplar because it does have a storage cost? And am I already inside of a traced context? If I am, then just go ahead and store the traced context if there isn't already a trace associated with this bucket. On the client side, if we're trying to collect these tags, we might say, by the way, this is not just for task level data, but I might want to say, what's the ID of this request? if you have some kind of logging system that stores log IDs, you can say, I want to record the context with this specific log line. And then when we do duplicate, we can say, look, I'm aggregating multiple different distributions together, and I can say, I'm going to see what are all of the exemplars that are associated with the things I'm aggregating, and then I can just randomly pick one, and not necessarily the first one that I see, and store that in the aggregated completed distribution result. And then when I'm sampling for cardinality, I just might want to say, if I would drop a tag, instead I'm going to pick one at random to keep. So to summarize about exemplars, the idea is that if you have traces or culprit tags or individual pointers to log data, it will give you a lot faster method of forming hypotheses of figuring out what's going wrong in your system. And just knowing which host or which request ID or which timestamp or which trace, that helps you track down your problems really fast. Like the method that was going on in Bigtable S3, the team I used to work on, was you used to spend 20 or 30 minutes staring at dashboards when you got paged. Not anymore, because you can go and just click on the trace, find the trace, go look at the right graph to start with. And that means that hypothesizing and testing gets faster. So just a note on what the public state of the art is here. Distributed tracing is in the wild. Distribution graphing is in the wild. And we're working with a large number of people to try to get this technique widely adopted across any observability suite that you might use. So I know, for instance, that someone has integrated, another APM provider is integrated with Grafana. We have this coming to Stackdriver, and I've also been talking to Honeycomb and other observability providers because this is really powerful. We need to all use it. It will save all of us time. It will save us headaches. It will make being in the cloud easier. And that's a win as far as I'm concerned. So to conclude, once you've cleaned up your incident, what do you need to do? Like, you need to log what queries did I write, export them out of the query editor into something more reasonable so that the next person who comes along might have an idea of how to start debugging a problem. But it's critical. Don't jump to creating a new dashboard. Do not do that, because you have just added technical debt. No two outages are exactly identical, and if you make it so that the next N outages also have someone staring 30 seconds trying to figure out what that graph is and how it might help them, that's not a good time. You're not saving anyone time. So we think that if you can reduce your time to resolve, it'll decrease the amount of error budget you spend, which will lead to happier users and you being able to ship features faster. You really have to have ad hoc querying and drilling down to be able to investigate hypotheses. And if you can quickly root cause things, then you're going to be a lot happier than someone that can't quickly root cause things. So a couple of pitches in our last couple of minutes. Check out OpenCensus, check out Stackdriver APM and Trace. And also, there's an entire talk dedicated to distributed tracing by Gina, so please attend that. And also attend my colleague Matt Brown's talk on how to measure your risks and prioritize what engineering work you want to do. Thank you.
Thank you.
I think we have time for 2 questions. 2 minutes, 2 questions. Step on up.
I can return this
microphone.
microphone.
Return the mic too. Going once, going twice, or I've stunned the crowd into silence. Either way. All right. Thank you very much for coming to our talk. And I'll be over probably by the Google booth during the break, so you can feel free to find me at any time. Thanks.